Good afternoon, everyone. Hopefully, everyone is staying warm. First torrential downpour we've actually had in the Bay Area in a while. Afternoon. Glad hopefully, everyone's safe and warm. Okay, so let's get started. Today, we're going to talk about light and optics. So we're going to connect all those electrostatics, electromagnetism things, both the electric field and the magnetic field together, permittivity constant, permeability constant, all that good stuff, and unite them together today for light and optics. So let's get started. First, we're going to talk about light and different light properties. Second half of class, we'll talk about optics. So in order to talk about light, we need to know that everything on the electromagnetic spectrum is considered a light wave, right? So an electromagnetic wave is a light wave, and what we consider light and what we see, the visible part of the electromagnetic spectrum, is only a small subset of the whole electromagnetic spectrum. So we have to know the whole E&M spectrum. We have your AM radio waves, FM TV waves. You got your microwaves, and then infrared. This thin sliver of what we can see is called the visible spectrum. That's what we can see, and this is where we get our colors of the rainbow, our Roy G Biv, right? Red, orange, yellow, green, blue, and violet, right? On the other end of the spectrum, you have UV, you have X-rays, and you have gamma rays, okay? The thing that I want you guys to know are their frequencies, because frequency later when we talk about equations, you'll see it's directly related to energy. So AM and FM waves are around 10 to the 6, FM and AM and radio waves, FM and TV waves are around 10 to the 9th. Microwaves are 10 to the 11th. The visible spectrum, the red, is around 4 times 10 to the 14th to around 7 times 10 to the 14th for the violet, for our visible spectrum. UV rays are around 10 to the 17, X-rays 10 to the 19, gamma rays 10 to the 21st. There's cosmic galactic rays, that's around 10 to the 23rd hertz. So remember, frequency is cycles per second. Everything on the electromagnetic spectrum travels at the speed of light, that's c. And so on this end, you have a large frequency and a small wavelength. And on this end of the spectrum, on the far left end, you have a small frequency and a large wavelength, okay? But they're inversely proportional relative to the speed of light. And we'll talk about the speed of light in a second. So everything on the electromagnetic spectrum is what we call an electromagnetic wave. So with the E&M wave, it has both an electric field component. We're going to draw both. So this is your electric field. I'm going to draw in a different color in a second. Your magnetic field. So it's going out of the board, into the board, out of the board, into the board, out of the board, into the board. So the green is your magnetic field component. The black is the electric field component. And what you notice is that they're 90 degrees relative to each other. Okay. 90 degrees to each other. Okay. Both the electric field and magnetic field components of the E and M wave. So every wave from AM, FM, microwaves, UV, X-rays, gamma rays, and visible light rays behaves like this electromagnetic wave. It has an electric field component and has a magnetic field component, both of which are perpendicular to each other. Okay. All right. Light travels fastest in a vacuum. The speed of light is 3 times 10 to the 8th meters per second. And we know that speed of light is equal to lambda f from the E&M wave. And the energy associated is Planck's constant times frequency. H here is called Planck's constant. I may or may not have gone over it, and that's equal to 6.636 times 10 to the negative 34. The units are joules seconds. Okay. This is your H, Planck's constant. And you can clearly see that energy is directly related to frequency. So what do we notice? The higher the frequency that we have, the more energy associated with our electromagnetic wave. And if you think about it, these are the waves, the higher, the far right end of the electromagnetic spectrum type waves are the ones that create cancer cells, right, or lead to deletions because they're more higher frequency. They also have a shorter wavelength, so there's more likelihood for it to like cause deletions, knockouts, and different types of mutations in our DNA from those types of waves, the UV and higher energy type waves. Okay, leading to all the different cancers that we have out there. Okay. The other thing we need to know is the speed of a wave in a medium is equal to the speed of that wave in a vacuum, which is c, divided by n, which is called the index of refraction. So this is the speed of light in any type of medium. And so as we have a higher index of refraction, so let's look at some indices of refraction. As we have a higher index of refraction, you're going to have a slower light traveling in that medium. And this has to deal with the transverse nature of your light wave. Remember, movement of material for transverse wave is perpendicular to wave propagation. So if you think about it, think of atoms and molecules being really close to each other. The more dense that medium is, the closer the atoms are, right? So the more dense that medium, the higher the index of refraction, because light can't continually go in and have that atom vibrate up and down and collide with its neighbors, right? Move up and down, because the movement of material is perpendicular, right? For your transverse wave. So that's why it has to bend around. And when we talk about light refraction, we'll talk about how light bends in a second. Let's finish off some indices of refraction that you guys need to know. It's 1.33 for water, 1.51 for glass, and 2.4 for a diamond. Okay, the most densest material that we know. So the more dense the medium, the more dense the material, or the greater the index of refraction, right, the slower light will travel in that medium because it's being bent more in order for it to go through that medium. Sorry, dry gas or dry air. So you'll see one being used for air all the time, and that's when it's dry. There's no humidity in it. There's no other types of interactions that will cause dispersion or light refraction. Okay. Sorry. I think I said it. I didn't finish writing it. Someone commented dry what? Vacuum and then dry. And I was like, no, dry air. My bad. Any questions so far? Okay. This has to deal with the speed of light. Oh yeah, you also need to remember that the speed of light is 3 times 10 to the 8th. Remember, this is also part of E is equal to mc squared. C is that speed of light. The other thing we need to know about light is light can be Doppler shifted. Thank you for keeping me laughing. And hopefully we understand that when we talk about a vacuum, that's just the lack of air. Okay. Not just the materials or the machine we use to suck up dirt in our house. So with dry air is different than no air. They consider it the same thing as a vacuum because we're assuming that the air molecules are all ideal and there's no interaction. Sorry, someone was like, how is dry air the same as a vacuum? They're assuming that for all intents and purposes that the molecules are not interacting with each other. Remember when we talk about ideal gases, they have no volume, they occupy no space, and there's no intermolecular forces. So they're just free flowing all by themselves, right? Good question though. So redshift. So we see this, actually, NASA scientists see this. I guess I can be considered one of them. I did work at NASA. So we see this redshift. This is when the object and source move away from each other. So, which means what? When things move away, frequency decreases in the system. So whether we look at other stars, galaxies, planetary bodies, we see this red shift occurring. You see it all the time, actually, when you view the Hubble telescope at natural things using just the natural camera. What scientists do is they phase shift it back so that you guys get these nice, pretty colors. Doppler effect, we already talked about Doppler when we talked about sound last week, right? That's perceived frequency changed when relative motion between a source and observer. Feel free. So for those who missed last week's lecture, feel free to stay after for office hours. I can explain those like little things like Doppler, and I can also send you lecture notes too at that time. You can just text me the email and I can just send you lecture notes from last week for sound and Doppler. So Doppler shifts occur when there's relative motion between a source and observer. Okay. The other type of shift, and we see this too when we look at comets and things that approach us, it's called the blue shift. The blue shift is when the object and source move towards each other. The frequency increases relative to the source and observer. So the source is generally another star in another solar system, in another galaxy generally, or even in our galaxy, right? And we are the object or the source, right? I mean the object, and we're observing it. We're the observer. Okay. So we see this all the time in reflected light coming off of like comets. Like you'll see Halley's Comet. They always have that blue aura around it. That's because it's blue light shifted due to Doppler effect. If you see a nice color picture of the comet, then that means that they phase shifted that color off, because all pictures that we get from Halley's and other types of comets that are approaching us, you're going to have that blue shift. Sorry, that's an interesting thing. So we had a student comment that, oh, is Doppler the thing that if you run a red light, you can say that you're driving so fast that it looked like so you are increasing frequency, right? But that doesn't change the the perceived frequency, but that doesn't change the color of the light to you. We're not going that fast. We'd have to be going closer to the speed of light, right? Nowhere in a vehicle, like you think about it, speed of light is what? 300 million meters per second. A typical car goes like what? Like 40 kilometers? No, like 80 kilometers per hour, right? So that's a really, really small speed. And what happens when we compare a really small speed with a really big speed? It's not going to make much of a difference. You can try using that excuse, and if your police officer is uneducated, which they shouldn't be because they have their own Doppler effect sensor called this radar gun, right? So they're using radio waves. We talked about this. They weren't using sound like we talked about last week, the Doppler effect. They're using radio waves, which are infrared, near infrared waves, and they're shooting them at you. They know their speed. They know the frequency at which they shoot at. They know the frequency that comes back to them, and therefore they can determine your speed, right? So that is not refutable in court. So if you're ever going to try to fight a speeding ticket, they just need the cop to show up and show you their radar gun on that day, because it records all their radars that they shoot and all the busts that they make. So it's proof. So it's pointless to fight a speeding ticket in court, or a red light in court as well, because they have cameras now. So just save yourself the time. You can hope the police officer doesn't show up, but there's no guarantee. Nice try, though. Trust me, there's things you can get away with and things that you can't get away with. Yeah, if you want, we can discuss in office hours how to get away from a speeding ticket. There's certain cars with certain windshield profiles that prevent radar from hitting and sticking to you and bouncing back properly. So they'll deflect the light rays that are shot at you at different angles. Sorry. I feel like for guys, there's like never a good way to get out of a speeding ticket. I feel like with ladies, it's much easier to flirt your ways out of a speeding ticket. I've seen my friend do it multiple times, and I was just like, what? We could never get away with that. Okay. So with polarization, so we're taking light, let's say light from like, say, a light bulb. It's going incident outwards in all directions. We'll call the light coming from that light bulb some I naught, or the intensity of light. So remember how we talked about intensity last week? Light intensity is same as sound intensity, right? It's some power divided by some surface area of it going across. Sure, I can go back to the last slide. Red shift is when the object and source move away from each other. Blue shift is when the source and the observer move towards each other, okay? In which case the frequency increases while we get a blue shift. And we're moving away from each other, we get this red shift. And you see it in other quasars, and you hear people talk about this red shift all the time. This is ever proof, the red shift, that the universe is ever expanding from the Big Bang Theory. This is where they got the Big Bang Theory, that the universe is ever expanding. And it's been proven that it's getting further and further away from each other from that Big Bang. Cool. Yes. Sorry. So there's certain cars you can get. It's usually out of the price range of most like newly graduated college students and even newly minted doctors. But you can definitely get it later in life when you have a little bit more money. That'll prevent you from getting like the LiDAR guns from working on you so great. So polarization is a physical filter of light. So what the filter does, it only allows certain components of light to go through. Remember, there's a vertical and horizontal component of light, both the magnetic and electric field. So when light is coming in, it's incident on those type of rays. So this type of filter would only allow vertical components of light to go through. And so what ends up happening, all the horizontal components of light get stopped. So the intensity of light is now half the intensity of light afterwards. This is typically called polarized light. So what the MCAT likes to do is put that polarized light through another type of filter. And that filter will be at a specific angle. So given the curtain that we have, this creates an angle of incidence from our vertical components right now. The other way to find the light intensity after it passes through a second polarizer is called using Malice's law. Intensity. I is the intensity of light. It's the same, watts per meter squared that we talked about for sound waves. Still in the same unit. It just tells you how bright something is, right? So before, when we talked about sound, we called intensity how loud something is. We called it loudness. But with light, it's how bright that light source is. Now, Malice's law, remember, is used only when passing incident light, which is the original I naught that I have, through a second polarizer. However, if we take polarized light and pass it through one polarizer, you can still use Malice's law as well. And Malice's law simply states that the intensity is the intensity of light that we have coming through, not squared, sorry, times the cosine squared of the angle that we make with that polarized light for the second polarizer. So this is Malice's law. The reason that we care about Malice's law is think of all the spectrophotometry that you do. And imagine if your molecules that you had in solution, after passing it through one filter to make it the light polarized, if it has optical activity or chirality from your organic chemistry molecules and there's freedom of rotation, those molecules that are freely rotating also will bend light like a filter. Correct. And the new incident light intensity uses the I from the previous filter. Correct. After passing through the previous filter, yes. So this would be your polarized light, that I naught that we're talking about, okay? So this is for polarization. So this is the only time that you'll have this come up. With optics and glasses, with the filters that we can put on glasses, we can have light be polarized as well. It reduces the blue light intensity, right? If you have a blue light filter, most people who are wearing glasses. Thank you, Monica. Second polarizer. Yeah, so you have to pass it through two filters. So polarizer is the same thing as a filter. by the way. Thank you. Okay, now let's take a look at dispersion. This is all the macro things that we're talking about light. We talked about speed of light. We're talking about Doppler shift. We're talking about energy associated with light, indices of refraction, and now another macro scale thing we're going to talk about is dispersion. So dispersion occurs in any substance in which the index of refraction varies with the wavelength. That's right. Different wavelengths cause different angles of refraction. Okay. So we see dispersion on the macro scale. So normally when we pass light through a prism, and you'll see it in certain types of glasses, as light passes through glass, as it shines through some glass in like a library. So let's just say this is your white light, but white light is consistent of all the colors of the rainbow. So think of red. It has an index of refraction of around 1.51. For violet, it has an index of refraction around 1.52, and then all the other colors are somewhere in between. Okay? So what you end up seeing is that for each of the different colors, they have different refractions. Sorry, I don't have yellow, orange, or violet. What you see is the higher, what we see here is that higher frequencies of light experience greater refraction. And this has to deal with the transverse nature of light. Remember how I talked to you about movement of it is causing the atoms to vibrate perpendicularly? So the faster or the higher the frequency, the less likelihood is that atom able to move back as it vibrates between the next atom closest to it and the one below it, on top and below. It less likely has a chance to go back to resting state or a relaxed state. So it stays compressed. So therefore light can't traverse through that medium, and because it can't move the material. So then in order for light to traverse, it has to bend to the next possible atom and vibrate those perpendicularly. Okay. And that's where we get light refraction from. So what we see as light dispersion is just macro scale refraction. So what we notice is that the lower frequencies or higher wavelengths don't get refracted, because when you think about it, the higher the wavelength is, the easier it is to move past small atoms within a medium. And it can like not have to allow that atom time to vibrate. Okay. Cool. So dispersion, macro scale refraction. Any questions on that? All right. Let's take a look now at what happens between an interface. What numbers? Oh, for red and violet? Yes. No, just know that there's varying different indices of refraction for all the different wavelengths of light within a amorphous medium, right? So in this case, we know that glass or some type of glass is always some type of amorphous medium. So it's always in motion. it's easier when you're dealing with things that are like a lattice structure. But when you pass light through glass, glass is amorphous. The reason that we know it's amorphous, if you look at your mirrors and you look at anything that's glass over time, especially like something like, I don't know, like your grandparents will probably have mirrors in their house, those tall ones that like flip. You're gonna find that material from that glass actually like is thicker on the bottom than it is on the top, because it creates like these ripples and those mirrors that you have in the system, because the glass moves down due to gravity. Yep. It doesn't seem like it's moving, but over time, like may say like 100 years, you'll see that glass move due to gravity. Yeah. If you study it, you're going to find out that glass is an amorphous structure. So you have to do the material science behind it, which is why I think like most pre-med should do material science, especially if you're going to do any type of like orthopedics for inside the body. You have to know what's compatible and what's closest to bone to mimic it. So knowing different types of materials and different types of polymers that they have out there can give you a better shot at like simulating like what a vertebral disc would do, simulating what the cushion between your knees would do, so people aren't bone on bone. Yeah, so sorry if I freaked anyone out that you guys thought like glass was like a solid thing. No, it's a amorphous solid, which is it's always in motion. I wish it was that easy. Someone says that mitochondria is the powerhouse of the cell. Can I be a doctor now? And I'm like, nope. Unfortunately, you can also be a botanist with that information. So let's take a look at the two things that happen between an interface when light approaches between an interface. So air would be N1, N2 would be, say, like glass, right? So this is less dense medium, and N2 is more dense medium. So we always draw the normal. So the normal being the perpendicular line between the two surfaces and the interface, between the mediums. The light ray that's coming in is the incident ray. Of light. It makes an incident angle. Two things happen at an interface between one medium and the next. The first thing that can happen, light can reflect. This is theta big R. This is the reflected ray. Law of reflection. Simply states that the angle that we come in at is going to be equal to the angle that we leave at. So theta I is equal to theta R. So the incident angle is equal to the reflected angle. Okay. The other thing that can occur, by the way, if we're going from a less dense medium to a more dense medium, the reflected ray flips. So if we're going from less dense to more dense, reflected ray flips 180 degrees out of phase. And we talked about phase in that nature when we talked about interference. If we're going from more dense to less dense, reflected ray stays in phase. Okay. The next thing that can happen, light can also refract. This is your refracted ray of light, and it creates an angle theta. We're going to call that little r. Okay. Snell's law of refraction. Snell's law of refraction simply states that the incident medium that we're coming in from times the sine of the incident angle is equal to the medium that we're going to times the sine of the refracted angle, theta little r. Okay? That's what this is right here, theta little r. Okay? So this is Snell's law of refraction, and this is the equation that governs what happens when we have light passing through a medium. And these two interactions that are happening at this interface, reflection and refraction, are both occurring, are going to be the basis on which we're going to be talking about our optics later today. For mirrors, we're always going to have reflection, but for lenses, we're going to have to deal with refraction. So there's going to be five optical devices that we need to know, your 3 mirrors and your 2 lenses, which we need to know. So we need to know our Snell's law of refraction for our lenses and our law of reflection for our mirrors, okay? For simple mirrors and lenses. It's lowercase. The R for the theta is lowercase in the equation. So this is a little r. And this was the capital R here for reflection. So reflection, I'm going to make it capital R. But the refracted angle, I'm going to make lowercase r. Okay, so you can differentiate between the two. So we know that theta little r is refracted angle or refracted light, and reflected light is the other light that's coming bouncing back. So if you think about it, a light wave and its energies get split. One comes through and part of it goes through and the other part of it comes back. It's only when you get total reflection do you get like all the energy of a wave of light coming back. Okay, so those are 2 things that can happen. What we need to know if we're going from a less dense medium to a more dense medium, the refracted ray, which we see here, bends towards the normal. And if we're going from more dense to less dense, the refracted ray bends away from the normal. Okay, let's keep that in mind. All right. By the way, definitely need to know the law of reflection, but it's really simple. Angle coming in equals the angle at which it comes out at, based on the normal, right? So the next thing that we need to talk about is called total internal reflectance. So total internal reflectance occurs only when going from a more dense medium to less dense medium. So only occurs going from a more dense to less dense medium. The reason being, so let's draw it out. So this is the interface between the more dense, which we'll call N2, and the less dense, which we'll call N1, right? So here's the normal. So if light comes in from the more dense medium, that refracted light ray bends going from more dense to less dense. We'll keep it the same notation. No, it could be arbitrary. More dense doesn't always mean N2. I just kept it that way because I called N2 glass, and I just said that medium is more dense, but it doesn't necessarily have to be N2. It can be N1 or N2, right? That's the beauty about like these equations. Those variables don't have to be fixed. They're always something else, right? Hence the variable nature. So if we keep on increasing this angle, we keep on swinging it out, you're going to notice that this ray keeps on bending further and further away from the normal, okay? So much, in fact, that at a certain angle, that ray bends exactly at 90 degrees to the normal, right? And this angle here is called the critical angle. So at theta C, which we'll call the critical angle, light refracts at 90 degrees. Okay. Why do we care about that? Because any angle greater than theta C reflects light only. So that means what? Total internal reflection occurs. So any angle greater than theta C, light completely reflects in the system. Okay. Why do we care about total internal reflectance? What practical thing do we use almost every day that uses total internal reflectance? Yay, fiber optic cables. Sorry, not mirrors. Fiber optic cables, right? So let's take a look at a cross section of a fiber optic cable. Yes, it's between the normal, so theta refracted would be here, and then theta C would be the incident angle, right? Or this theta could be the incident angle. So if we look at our fiber optic cables, what ends up it looking like? Looks something like this. So there's a doped silicon. And then this is your pure silicon. By the way, silicon is derived out of quartz, and quartz is just sand. And all you have to do to get the silicon dioxide or the oxide part to come out is just heat up that quartz or the sand, and you'll end up getting pure silicon. The oxygen gas comes out from SiO2. Nice to know about material science. And so if you think about it, if we shine light in at an angle greater than the critical angle, then that angle can be totally internally reflected. And if we think about it, every wireless technology that we use uses fiber optic cables, whether it's your cell phone, your computer, your laptop, right? It's being broadcast through fiber optic cables with the light coming on and off, on and off, on and off. All that light flickering that you see is the actual signals turning on and off, on and off, and on and off, and giving you this binary or quaternary structure to have signals systems transmit, right? What you guys think of as magic, right? Your Bluetooth, your Wi-Fi, your cellular network, they're all using fiber optic cables. In fact, I believe with broadband now, there's enough fiber optic cable to wrap around the earth 11 times over. It's pure silicon. And then the other one is doped silicon. It's doped with impurities, because that just means that it's more dense. So to make that medium more dense, we dope it. Yeah, so fiber optic cables are used to transmit signals across and create the whole World Wide Web and how data is transmitted, right? Even if you think about it, your cell phone, you're like, nah, there's no cables connected to my cell phone, Khoi, you're crazy. Your cell phone goes to, it's defined, critical angle is the angle at which light refracts at 90 degrees. That's in red. Right? Any angle before that, light is bending at some angle. That's what the black color is. And any angle greater than that is the green color. And that's totally internally reflecting. Hence why I drew it again in green here in the fiber optic cables. But fiber optics allows us to transmit data, right? One being on, and then you'll have certain sections where it's off. Right? How does your cell phone have fiber optic cables? Sorry. So what it ends up doing is you have a short range wireless communication to a satellite, right? And that satellite is connected to the World Wide Web via fiber optic cables, right? So those cell towers that we're generating signals everywhere for inside the city, isn't it labeled theta C? That's what theta C is.
It is labeled, but like which angle is it?
The one for the red.
Oh, okay, because it was in
Red.
black.
Sorry. Yeah.
And then what is so the bottom one is the incident angle?
Yeah, and all of this can be any of these angles or incident angles, right? The critical angle is a specific angle that will get light to refract at 90 degrees.
So because that red line is beyond the 90-degree angle, we have a critical angle.
The red line ray creates the critical is the critical angle because light refracts at 90 degrees. Any of these right rays coming in, any of the incident rays coming in, the black, the red, the green, would normally create refraction, right? And so what ends up happening is at a certain angle, you get light to keep on bending away until it refracts at 90 degrees. Light can come in at any incident angle. I just drew 3. Should I color it, code it too with different incident angles? But it just seems redundant. I feel like you're still confused. Where are we confused at?
If it's for me, I can ask you offline because I'm really lost and I don't want to like have to take a whole bunch of time to get through it during class.
Okay, we can do it after class. I'm just like this last picture that I originally drew, because just an incident angle. And then you have a refracted angle. For every incident angle that you come in at, you have a refracted angle.
Right.
Okay, so that's why this general equation could be for any angle that comes in. And I just happened to draw 3 of them for this picture: the black one, the red one, and the green one.
I'm just having a hard time seeing the critical angle in this regard. So is the critical angle the the one that occurs on
The one in red.
Yeah, there's just two lines.
This is the refracted ray that comes about.
Okay, that was where I was confused. Thank you.
It literally says light refracts at 90 degrees. Sorry, like, I don't know how else I can explain that, right? So
I was just confused. I apologize.
Yeah. No, so when the light ray comes in at that incident angle that happens to be the critical angle, light refracts at 90 degrees. If it came in the black one, it refracts at a certain angle, right? That's your refracted angle. Snell's law will define that. Okay.
Hey, Khoi, it's Lexi. I just wanted to comment that I was a little bit confused too. And I really appreciate Michaela bringing it up because now it is much more clear. So thank you for that, Michaela.
Sorry, I should have drawn the angle in red as well when I labeled it. Cool. Did I answer the question about the fiber optics cables and how fiber optics is used for all our Wi-Fi? And why
You
it's
did, and
important?
thank you.
Okay, that's how the World Wide Web is connected. We have enough fiber optic cables to wrap around the Earth 6 times over. Sorry. Oh, okay. Kind of like how you guys wrote that letter about the teachers, right? That's some compassion, right? Just saying, goes both ways. All right, let's talk about optics. Oh, there's a question. Can you ever have reflection from less dense to more dense medium? Yes. So in general, there's both things that happen, right, at an interface between reflected and refraction. So if you're going from less dense to more dense, the light ray kind of splits or not splits equally, but you have two things happening. You have a reflected ray and a refracted ray. But total internal reflectance, if you want all the energies from your incident light wave to be saved and it doesn't split between reflected and refracted, then that reflected ray, it only happens when you're going from more dense to less dense, to answer that question. But yes, it can have reflected going from less dense to more dense. This is this slide. Okay. Okay, so let's deal with optics. So with optics, there are lenses and mirrors. Okay. Thing we need to remember is the thin lens and mirror equation. One over the focal length is equal to 1 over the object distance from the device plus 1 over the image distance from the device. We'll label F, O, and I in a second, but this is the equation that you're given. The other equation that you need to know for your optics is your magnification. Magnification is simply negative I over O. That's a general equation for each. So we need to know both equations, and we're going to define each one of these terms in a second. It's not theta, sorry, it's O. Object distance from the device, I is image distance from the device, and F is focal length. Okay? All right, let's take a look at what each one means. So F is your focal length. O is the object distance from the device. I is the image distance from device. And M is your magnification. Okay. Each of these are positive. Focal length is positive whenever you have a converging device. Positive when you have a real object. Positive when you have a real image. Magnification is positive when it is upright. It's negative when you have a diverging device. It's negative when you have a virtual image. Negative for the image, an object, or a virtual image. And it is, if magnification is negative, it is an inverted image. Okay. So, need to know each one of these terms. F is your focal length, O is the object distance from the device, I is the image distance from the device, M is your magnification. It's positive when you have a converging device, when the object is real, when the image is real, and when magnification is positive, it's considered upright. For all images created, they are either inverted and real, which is how we see, or they are upright and virtual, which is all the majority of the images that are created from our optical devices, okay? So, when dealing with optics, there are 4 questions that need to be answered. Sorry. Here you go. You guys can let me know when you're done. There's 4 questions that need to be answered. The first is, where is it? Second, is it real or is it virtual? Sorry, this is a V. For some reason, I'm writing it very much like an R. Third, is it upright? Or inverted? Or last but not least, how big is it? So look at the magnification, right? So where's the image that we're going to create from our object going through our optical device? Is it real or is it virtual? Is it upright or inverted? And how big is it? Okay. So we're going to have to be able to answer all those questions using our thin lens and mirror equation and our magnification equation. Okay. Let's take a look at our optical devices. Our mirrors. Oh yeah, we're gonna go over what real and virtual are in a second. It's gonna become apparently obvious when we talk about it in terms of mirrors, and it's gonna become obvious when we talk about it in terms of lenses, right? So with mirrors, sorry, someone asked what does virtual and real mean? Sorry, I was just answering that. It seemed out of context because I was just referring it to what we're going over. So the first thing that we need to know about mirrors is the focal length is simply the radius of curvature divided by 2. Okay, so that's your focal length. We use this equation typically for mirrors. There's 3 types of mirrors that we need to know. The first is the plane mirror. So always draw your device. It's good to make a sketch. Here's our optical axes. Here's our object. Okay. So when we're drawing any type of rays for our optical devices, the 2 rays that we draw are the one that goes parallel right above our head. So this is, imagine you looking at yourself in a mirror. This is the plane mirror that you look at when you get up in the morning. So the first one is the one going towards the device, perpendicular, right above your head. Since this is a flat plane mirror, it's going to reflect coming back out in the same direction. The other light ray is the one that goes right above your head, right to the center of the device. Law of reflection says that it's going to come out to be the same. Okay? So, since these 2 rays are going away from each other, this ray here and this ray are going away from each other. Those are the real rays. We know that the plane mirror is a diverging device. So all the real rays of light that we generate are always going to be going away from each other, right? So we know that we will never see an image on the same side as us because of that. So we have to extrapolate back where these 2 rays intersect. We're going to form our image. For mirrors, it's real easy. The same side that we are on is considered real. Anything behind the mirror is considered virtual. So if you can't block the rays of light, right? You can't ever reach back behind the mirror and go, look at that person. He's awesome. Looks great, right? Or you look perfectly fine. Or, oh my God, my hair is all over the place. You can never reach behind the mirror to look at that. So that's why it's considered virtual. Anything in front of the mirror is considered real. Does that make sense for the person asking what's real and what's virtual, right? So for optical devices, anything that where the real rays would have intersected is considered real. And so the reflected rays that we have from a plane mirror never intersect, so we'll never have a real image. So we have to extrapolate it back, and that's why you see an image of yourself some equal distance that you are from the front. And that image, you'll never be able to reach behind the mirror and get it. So that's why it's considered virtual. Does that make sense for real versus virtual? Okay. Correct. All plane mirrors are diverging. Any two rays that you draw will always be going away from each other. Right? Even if they have the different angles coming in, those angles will reflect equally, and those two rays will then go away from each other after they reflect. Yeah, so the actual rays, if you think about it, are the ones that I highlighted in green. Those two rays will never intersect each other. So you'll never get an image on the real side, the same side that you are. You are the object. That's you. So that distance from the object to the mirror is O. And I is the distance from the image to the mirror. Correct. Real images are created from real rays intersecting, not this extrapolated rays that intersect behind the mirror. So extrapolated rays, virtual rays, so to speak, will create virtual images. Haha, that's a good question. So if you think about it, for a plane mirror, the focal length is infinitely far away, right? Because a plane mirror is just a flat piece of glass. There's no radius of curvature on a plane mirror. So that's where we get the 1 over infinity is equal to 1 over O plus 1 over I. And where we see that I is simply negative O in our problem. Because 1 over infinity is basically 0. Sorry. We had a really good question come in where's the focal length here? Right? Because there's no rays that intersect with each other that pass through the optical axis. Does that make sense? Yeah, so a flat piece of mirror will have no radius of curvature. No radius of curvature. The only way you would assume that there was a radius of curvature is if that radius or that focal length was infinitely far away for this flat piece of glass. Correct. Sorry, there was a comment. Same idea if you see your reflection in a puddle. Yes, any reflection that you see in the water surface is similar. It just happens to be reflected better from a partially silvered or silvered mirror than, say, water. Same premise. So divergent device, right? Because you clearly know that you're not like, a few feet below water or underneath the water surface, because you know that you're above the water surface. The second type of optical device that we need to know, right? Do you recognize how that's a virtual view now? Because it was underneath the surface, and like how the mirror creates a image of yourself behind the wall of your house. So that's why it's virtual, because you'll never be able to get there. There's no such space that exists there. The second type of mirror is your spherical mirror. And there are two types of spherical mirror. The first is your concave mirror. So the concave mirror looks like so. Okay. We'll generate our object. So you are standing some distance in front of this concave mirror. Sorry, this isn't the concave mirror. This is the convex mirror. My bad. We'll deal with the concave mirror in a second. Parallel light ray that hits in. Realize that this is the concave mirror. Law of reflection tells us that it reflects out this way. So this would be your normal. So this angle is equal to this angle. Okay. The other ray is the one that goes to the center. It is still going to follow Snell's law of reflection. This is going to be equal. You notice that this ray and this ray are moving away from each other. So the convex mirror is a diverging device. Okay. So we then have to extrapolate back, and where the parallel light ray that came in intersects from that reflected ray, we form the focal point. The other ray will come through. Where those two rays intersect, we form our image. And what do we notice? For diverging devices, the image is always going to be virtual. Okay. Actually, for any curved diverging device, it's actually going to be smaller, upright, and virtual, SUV. Okay. So this is true for curved diverging devices. So this is the uninteresting case. It's always going to be that case. All right. Let's clear this. Sorry. Let's go through and deal with the convex case, concave case. Sure. This is the convex mirror. Smaller, upright, virtual, SUV. SUV stands for smaller, upright, virtual. So for the concave case, so the concave mirror looks something like so. Here's our optical axis that we need to draw. Let's draw our object. Okay. Parallel light ray coming in. It's going to hit. It's going to reflect. Where it crosses is the focal point. Twice that distance, r, is the radius of curvature of that mirror. The other ray that we need to draw is the one that goes right towards the center. Where these two real rays intersect, we get an image. Look at that. We actually have image intersection with real reflected rays, right? These are the real reflected rays that we have, and they actually intersect. And what do we notice? So first of all, they intersect. So this is a converging device. And with that convergence of light, what do we notice about this image that we've drawn that's different from the other images that we've drawn up till now, right? This image was upright and virtual. This image is upright and virtual. What do we notice about this last image? This is inverted and real, okay? So we take a look at our object, the image, and the magnification associated with each. So the converging device is unique. With the converging device, you can get inverted real images and upright and virtual images. So we need to know when that occurs. So when we're beyond R, the object, the image is going to be between the radius of curvature and the focal length. Magnification is going to be inverted real and smaller. Now, if we move our object in, and now that object is at the radius of curvature, so let's erase this reflected ray here and here, so we can draw our next one. That reflected ray, the one that goes right in towards the center of the device, will come out like so, intersect the device, the other ray right here, and you're going to form an image right where the object was. So at R, we're going to form an image at R. It's going to be inverted real and the same size. Now, if we move continually inwards, we're going to erase these two rays. We move inwards. Say here's our object. Two rays we're going to draw. So you notice that your object is going to be somewhere back here. So when your object or your image is going to be somewhere back there, not objects. Sorry, my bad. So when the object is between R and F, the image is going to be beyond the radius of curvature. It's going to be inverted real, and it's definitely going to be larger in size. Now, if our object is here at the focal point or focal length, so when our object is at the focal point, we have no image. The reason being, we draw our rays here. These two rays are going to be completely parallel with each other, this one and this one. So, do you ever walk towards a funhouse mirror or a concave mirror? As you get closer, you look bigger and bigger, right? And then what happens? All of a sudden, you disappear, right? This is when you're at the focal point of that mirror, okay? Because the rays that are coming and hitting are all parallel, they will never intersect, and no intersection leads to no image. Okay. And last but not least, oh my gosh. Last but not least, if our object is inside of the focal length, let's draw it out. The only ways that they'll intersect, somewhere back here, forming an image here. So if it's inside of F, the image that we create is behind the device, it's upright and virtual, and it is larger. Okay. So this is only true on a converging device. All diverging devices are going to have upright virtual images, always, no matter where you move that object. But this, what you notice from this, the black, the red, the yellow, the green, and the blue is your object moving closer. As you move closer, what happens to where the image is? It's all listed out there. And M is the magnification to tell you the type of orientation for your image, whether it's inverted real or upright and virtual. And once again, for mirrors, anything behind the device is considered virtual. Anything in front of the device is considered real. Any questions on that? Okay. Let's now talk about lenses. So those are the three mirrors that you guys need to know for your MCAT. So focal length depends on the radius of curvature and the index of refraction. You have that equation on your equation sheet. It's called the lens maker equation. Please remember that equation. But majority of the time, you're going to be using the thin lens and mirror equation, the one that we've already gone over. So depending on if your glasses are thick or not, you'll have to use the lens maker equation. Realize that the power of magnification is simply 1 over the focal length. I sent the equation sheet to everyone. Everyone should have that email. That was on week 3. Sorry. I don't know it off the top of my head because I find that it's not important for your MCAT. But it has come up in the past. But yeah, I hadn't had to deal with it for the last 5 years, ever since they switched to the non-paper version. But they have it just in case for the paper version. They used to have the lens maker equation. So for power magnification, that's 1 over your focal length. This is how your glasses are measured. If you guys have your myopic, i.e. nearsighted, or hyperopic, i.e. farsighted, you have your prescription given in positive or negative diopters, okay? If you're nearsighted, you're gonna have negative diopters. If you're farsighted, you're gonna have positive diopters. It's just past where your fovea centralis is in your eyeball, okay? And also realize that that power of magnification is additive. If you have multiple glasses or you have your contacts on and you put on a pair of glasses, you increase that power of magnification for your glasses, okay? So just keep that in mind. So now let's take a look. Actually, -4 is nice. Like I'm actually -5 1/4 and minus in one eye and -5 4 and 3/4 in another eye. So I'm hyperopic. I'm myopic too. It's good to know your prescription. Actually, I think it's all genetic. So my eyeball hasn't changed its shape, or my physical body hasn't changed shape, and I haven't had to deal with any type of lens changes since I was like 21. So I've been at this power magnification since like I graduated college. Actually, doesn't get worse over time. If anything, it gets better over time, and I'll talk about why. Yeah, so inverted and real. So remember, when we talk about the cornea and the lens inside your body, they're both converging devices that focus. They're both convex lenses, and they're both converging devices that focus light. and create inverted real images, because you generally see something that is an object really, really far away from your focal length for your eye. So it's always going to be inverted in real. Yes, the human visual system is inverted in real. All devices that we use to take these pictures and stuff are also inverted in real. You have to invert it back for us when you look at a photograph or any type of image that we take, even from the Hubble, right? They're always like inverted real. And old school cameras are simply like that as well, if you actually had to develop film and stuff like that. Yes, you have a cornea and a lens. Those are the two lens system that you have in your eyeball. The cornea and the lens are both convex lenses, okay? So let's just deal with the convex lens first. So the convex lens is very similar to the concave mirror in that it's a converging device. So a convex lens looks like that little bulb that you have. Looks like a magnifying glass, right? We always draw our optical axis that goes through the center of the object, of the device. First ray that we care about is the one that's parallel. So with lenses, what do we notice? We have light that is incident on an angle. This is the perpendicular to the device. You'll see light refracts from that device. I'm just going to continue drawing it further out within your system. Okay? So there's your focal length or focal point where it intersects. Remember, where the parallel light rays intersect is where you create your focal point. Realize that light can come in from either side of the convex lens. And so that's why when you look at these types of pictures, they always have two focal points within your system, or two focal lengths, okay? So the second light ray is the one that goes right through the center of the optical device. Where those two rays intersect, we form an inverted real image, right? Notice if the object is outside of the focal length, you're going to get an image that is beyond the focal length. Except for lenses, light goes through the device, so you expect the image to occur on the opposite side. So the real side for the image is the side opposite or behind the device now, because light goes through, because real rays go through. Now, if we draw on the other case where the object is inside your focal length, this light ray and that light ray for the parallel, this one and this one will never intersect. So you end up having to extrapolate it back. Where those two light rays intersect, we form our image, and then you notice that this is an upright virtual image that we have here. Okay, so remember that your convex lens is a converging device. So all the things that we discussed from the concave mirror are going to be true. Okay, so just keep that in mind when we look at the convex device. Okay. By the way, this is the type of reading glasses that your dad squares. Yeah, it's flipped because of the refractive nature and the reflective nature of a mirror versus a mirror versus a lens, right? Correct. One allows light to go through, the other one reflects light. So the lens allows light to go through and we deal with refraction, and the mirror reflects light. So that's why they end up getting flipped. To get a real image, it's always going to be behind the device for a lens, right? Or in front of the device for a mirror. To get a virtual image, it's always behind the device for a mirror, and to get a virtual image, it's always behind the device for the mirror or in front of the device for the lens. Sorry, had to think about it real quick before I say it out loud. Any questions on the convex lens? So all these things that we said here for the concave mirror with the beyond R, at R, between R and F, at F, and inside F, this is also going to be true for your convex lens. I just didn't take the time to redraw the same things. I only drew the beginning and the end, so you can see that the whole spectrum is still going to be the same, except for a lens, it's always going to be on the opposite side to create a real image. And if it's on the same side, then you're going to have a virtual image. So it's flipped. It just has to deal with that nature of reflection versus refraction. Reflection for mirrors, refraction for lenses. Okay. Okay. Let's clear this one. So let's take a look now at your concave lens. So with your concave lens, it has that hourglass looking figure. And this is the lens that we end up using for people who are nearsighted or myopic. We'll talk about why in a second when we talk about myopia and hyperopia. So here's your object. Parallel light rays that come in will refract light going outwards. Sorry, that's not correct. Exactly adequate. Where those light rays extrapolate back, we create our focal point. The other one is the one that goes right through the center of the device, goes completely right through, where we extrapolate back, and where those two rays intersect, we form our image. So notice that this ray of light and this ray of light are going away from each other. So this is going to be a diverging device. Okay. So it's always going to refract light away from each other. So once again, what do you notice? We have a curved diverging device, and that generates what? A smaller upright and virtual image, right? SUV for your image, smaller, upright, and virtual. All right, so let's give you guys a quick question, getting you thinking about our lenses. Actually, let's do one more thing before we talk about, actually, let's give you the question first. So, first question of the day, we have an object is placed 30 centimeters away from a concave mirror with a radius of curvature of 20 centimeters. Do you remember those 4 questions I asked you to answer? I need you to answer them now. So describe to me the image. Where is the image? Is it real or virtual? Is it upright or inverted? And how big is the image? Using magnification. So we know the object distance is 30. We know that the radius of curvature of the mirror is 20, which allows us to find focal length. We need to find the image distance from the device. And from that image, we can dictate where it's going to be. So find me I. Is it real or virtual? Upright or inverted? And magnification. Yes. I was very confused. Yes, we actually have to do some numbers and crunching and some physics. As much as we like to keep everything like qualitative, we have to do some quantitative here. That is true. Numbers, please. Numbers, please. We need to know where the image is. Is it real or virtual, upright or inverted, and the magnification. How big is it relative to the object? But I'm very happy that a lot of people said smaller, inverted, and real so far. This is very, very good. It is inverted, real, and it's smaller. Correct. Right? So that's why knowing that table that I did with all that colors, it's going to give you a general range of answer choices already. Do you see? That's why I spent time doing it, because this is going to help you on those multiple choice type questions that do arise from this, especially when you have a converging device in your system. So we know O is 30 centimeters. So sometimes for finding the image distance from the device, it's easier to do O cross F over O minus F. Another 30 seconds and then we'll get through the answer. But I want everyone time to build those neural pathways, apply the math and equations that they've learned. Yes, we've done a lot of qualitative things today, but we still need to put it to the quantitative to practice. Okay, I think that's enough time. The majority of people have chimed in. So we know the radius of curvature is 20. So what's the focal length? R divided by 2, right? Or 10 centimeters. Good. So let's do our check. We have a concave mirror. Concave mirror is what? Converging device. Our object is outside of our focal length. So we're expecting to get an inverted real image, right? Let's see if that works. So 1 over 10 is equal to 1 over 30 plus 1 over I. So 1 over 10 minus 1 over 30 is equal to 1 over I. So find the same common denominator. 3 over 30 minus 1 over 30 is equal to 1 over I. So 2 over 30 or 1 over 15 is equal to 1 over I. So I is equal to 15 centimeters. Because 1 over I is equal to 1 over 15. So I is equal to 15 centimeters. Or you could have just said 30 times 10 all over 30 minus 10. 300 divided by 20. 30 divided 2 is also 15 centimeters. Cool. So what do we notice? It is a positive 15. Positive tells us what? It is real. Image is positive 15 centimeters. Magnification equation tells us that's negative I over O. So that's negative 15 over 30 or negative 1/2. So negative tells us what? It's inverted. So reality check checks with the math. And now it's half as big as our object, right? You can also check by drawing a little sketch. Always. So here's your concave mirror. Here's your object. Parallel light rays that come through. Right, there's your focal point. Sorry, this is the one that's supposed to go through here, right? This looks like it should be half as big as that, inverted in real, right? Slightly further than 10. Reality checks with our sketch. We should be very happy. Any questions on that? Oh, this equation here, I just gave you a shortcut to deal with a thin lens mirror equation. So all I did was what? Find the same common denominator. I take the object and the focal length, multiply them together, and then I get the difference between the object and the focal length to solve for the image. Okay? That's all. Nothing special. This equation just helps me find it. Oh yeah, remember that table that we had? Plop. Positive, it's real. Negative, virtual. Negative for magnifications, inverted. Positive for magnification would have been upright. Converging device gives me a positive focal length. Diverging device gives me a negative focal length. This is why I went over it. Correct. See, things that I put out in during lecture, they always end up getting used, and it always comes back. So, thank you for asking. No worries. Totally understandable. So let's change this a little bit. Instead of having a concave mirror, we're going to get a concave lens. Instead of giving you the radius of curvature, I'm just going to give you that the focal length is 10. I want you to describe to me this new image. So we'll change this. Is now problem 2. We have an object that's placed 30 centimeters away from a concave lens with a focal length of 10 centimeters. Describe the image. I'm going to let you guys copy that down from the previous question, then I'm going to erase it in like a minute while you're doing this one as well. For those who haven't finished, you can copy it down. This is how we use that table I gave you, thin lens and mirror equation, and your magnification equation to solve questions on images. Leave the equation around. Describe to me the image. It is not the same. For those who are saying it's the same. What type of device is the concave lens? Is it converging or diverging? Subtle changes, subtle changes. It's easy to miss. Now we're dealing with the lens. about a minute, so we have time to go over this, and then I can give you a quick lesson on myopia and hyperopia, and then we'll do a passage. All right, I think that's enough time. So what happens to the focal length when we have a diverging device? Is it positive or negative? It's upright and virtual, that's for sure, because this is a diverging device, right? Diverging devices always give you upright and virtual images. Okay, so let's make sure the math matches. So focal length is actually a negative 10. They won't tell you that, but you need to remember that, okay? So the object is 30 times a negative 10 all over 30 minus a negative 10. So negative 300 divided by 40. So 30 divided by 4 is 7.5. So negative 7.5 centimeters. Okay. So negative will tell you what? It's virtual. Magnification is simply negative I over O. So that's negative of a negative 7.5. O is 30. So that's going to be equal to a quarter. And it's positive. You notice positive tells us what? It's upright. So it matches with what we expect for a converging device, upright and virtual. And we clearly see that the image is further out or inside of the focal length that we get in our system because of our divergent rays intersecting back. It's going to be a lot closer than where the focal length and object are in your problem. Okay. Any questions? All right. Let's go over myopia and hyperopia real quick, and then we'll do your passage of the week. Myopia, this is nearsightedness. For some reason or other, here's your eyeball. Due to either the eyeball shape being too long or the cornea and the lens, this is your lens. It's connected together through your zonular fibers. This is your cornea. Parallel light rays that come in for myopic people. So here's your optical axis, by the way. At the back of your eye, this is where the fovea centralis is, otherwise known as your retina. Nearsightedness means that you can see only near. So people who are nearsighted can read things perfectly fine. They just can't see jack on a whiteboard in class, right? So you only need your glasses to see far away, right? You can't see the street signs when you drive, but reading a book, totally fine. Nearsighted people, myopic people. The reason being is, for some reason, you focus light ahead of the fovea centralis or your retina. Due to your eyeball being too long, your cornea and your lens system together being too convex. it's focusing light too soon. So parallel light rays that come in get focused too early. And for hyperopic people or farsightedness, right? Due to your eyeball being too short, or later in life, you see your parents needing reading glasses. So for some reason, your cornea is not convex enough, and it focuses light behind the fovea centralis or your retina. Okay, so hyperopic people, optic, hyperopia, are people who focus light way too far behind their retina or fovea centralis. So to correct for hyperopia, we always have to put in front convex lens. And to correct for myopic people, we always are going to wear a divergent lens. And if you think about it, the reason that we can read things up close is because the rays that are coming in from things that are close near our face are divergent rays. So those divergent rays naturally push light back, right? And increase our focal length, right? And for those rays specifically. But parallel rays, they get focused way too far in front. Okay. So to correct for myopia, you always have to wear a divergent lens to correct for it. For correcting for hyperopia, you have to wear a more convergent lens to pull that focal length up close, to refract or bend your light rays more to get it to focus earlier. Okay. So what happens? Why do your parents need reading glasses, right? I always find it hilarious that my dad has to ask my mom to hold the menu up when they go out to eat from the other side of the table so he can read it, because he refuses to wear glasses. He thinks that wearing glasses makes him look weak, right? That old mentality. I wear glasses. I think you guys seen me. I find it hilarious. Yes, divergent lens for myopia and convergent lens for hyperopia, because convergent lens focuses light sooner and forces it to pull that focal length up, or that focal point up. So it focuses light right at your fovea centralis or at the retina. And divergent lens pushes that focal length back from those parallel light rays. So it focuses light at your retina. Oh my. I Sorry, can't type in and talk at the same time. Someone's saying that they're having bad connection and can't hear. Yeah, so sorry about that. Inclement weather generally does that to us. Hopefully it's not affecting, diffusing their signals too much. Okay, so what happens as you get older, these zonular fibers get weaker. And when you get weaker, what ends up happening is the lens that you have is generally convex. It begins to flatten out. So it has a convex nature. So as those muscles relax, that lens flattens out and it pushes the fovea centralis, it pushes the focal length back. This is why your parents need glasses as they get older, okay? Or reading glasses. So these generally have positive diopters. This is negative diopters, right? For the type of lenses that you have in the front. Okay, so what LASIK does, so here's your cornea. LASIK takes a laser and makes your cornea less convex. So that new red is your new cornea, and it's flattened out. And when it does so, for people who are myopic, it pushes that focal length back. Does that make sense? So the only problem about that is, since it's shaving off nervous tissue, by the way, cornea and lens, nervous tissue, those tissues don't regrow. So it's permanent. So if you're going to get LASIK, do it for the right reasons. Go to a good person that does LASIK. At this point in time, the computer does everything, and your ophthalmologist only has to do a few measurements, and it's all digitized now. But always go to a good ophthalmologist. Make sure that they can catch any errors and fix it as well. Okay. So LASIK makes your cornea less convex and more flat, which pushes that focal length. So if your focal length was here, it pushes that focal length back. For your lens. So then that's how you get perfect vision from things that are far away. However, with the reduced, yes, makes it less convex, correct. And however, with the reduced thinner cornea, your eyes end up becoming sensitive to wind, sensitive to light. And so I find that people who get LASIK, they can't handle like the sun at full like exposure, and they have to wear sunglasses outside. So I still find it funny. I mean, it'll help you in a room, like in a classroom setting. You won't have to wear glasses anymore. And also when you drive, you don't have to wear glasses. But when you're exposed to high intensity of light or exposed to high winds, you end up having to wear glasses or sunglasses anyway. So, yeah, just I'm still not a fan of this. When I was your guys' age, I think like an undergraduate in college, I was really interested in not having to wear glasses. I came up with multiple ways to deal with this. LASIK was an option at the time. I think it was called wavefront surgery. But now I even came up with a corneal ring segment implant that I would embed in your cornea. Except if you rub your eye, then the surgeon would have to go in and re-implant it again. It was a research project we did. It was highly successful. I did it with an ophthalmologist and material scientists as well. And it was actually pretty cool. Got published, but just got no traction because people can't stop from rubbing their eyes due to allergies, due to getting dust in them. And every time that happened, the corneal ring segment implants that we implanted in your eye here and here to flatten out your cornea was getting shifted, and then that changed the curvature of your cornea. And I just wanted something less permanent than LASIK, because once you shave off that part of your cornea, right, with a laser, it's done. Like, it's permanent. It's never going to regrow. And your cornea is like thinner, could subject you to certain like eye diseases if you get like certain bacteria in them, because it crosses that blood brain barrier a little bit easier across your eye too. So we were just trying to find something that's an alternative to LASIK and a competitor to LASIK at the time. I mean, scientifically it was sound. It's just practically wasn't sound. Okay. All right. Any questions with that said? So I think, if anything, this would be the most applicable thing for most of you. I think most people wear glasses, especially people in higher education. Like, I know that's like a generalization, like up the wazoo, but like I found that like everyone that I went to college with, like either had contacts or had glasses. Like so, so generally, if you are okay, people wear glasses for the smart look. I mean, you think about it. It's chic to be nerdy now, right? You see, Dwayne Wade like wearing glasses without lenses in them, right, to have the shape. So, so for the student that can hear now, let's talk about myopia and hyperopia review really quick. Myopic people need a divergent lens to push that focal length back. And hyperopic people need a convergent lens to pull that focal length forward. Okay. So you wear a concave lens when you're myopic or nearsighted. And for hyperopic people, you are wearing a convex lens or a converging lens to pull it forward. What LASIK does is it flattens your cornea and it pushes that focal length back. Okay. So wavefront surgery or LASIK is what pushes that focal length back. Okay. So hopefully that makes a lot more sense in terms of what devices we're using. So if you think about it, we've gone over 5 devices today, 3 of which are diverging devices, the plane mirror, the convex mirror, and the concave lens. There's 2 converging devices, your concave mirror and your convex lens. And between the convex and concave mirror, you can have both inverted and real. All diverging devices only give you upright and virtual images. Okay. All right. With that said, let me pull up your passage. Give me a second. Jesus, where'd my sorry. The new iOS has everything like in a different spot. Cool. There are 7 questions. I will give you guys share screen real quick. Eight minutes. 1 minute warning before the end. Thank you. You guys have 1 minute. All right. Time is up. So, answer for number 8 is B as in Bravo, 9, A as in Alpha, 10 is A as in Alpha, 11 is D as in Delta, 12 is B as in Beta, 13 is C as in Charlie, and 14 is B as in Beta. Okay. So, sure. 8 was B as in Beta or boy, A as is an Alpha. 8 is B, 9 is A. Okay. So if you guys have questions, I'll be here to answer them. Otherwise, I will see you guys. Actually, I will not see you guys. This is my last lecture. Sure. I'll put it back so then you can screenshot it yourself. Here's the passage. But this will be my last lecture with you guys, and I think this is the last lecture at Berkeley Review for me. Other teachers will have different classes, but I think this is it. End of the road. So hopefully you guys got your screenshot for 14, and it's been great this past semester. Thanks so much for being good students, always asking questions. Yeah, no, it's sad, but I think this is also my last lecture at Berkeley Review too. I think Todd's letting everyone go, according to Todd. So, but I will talk to you guys. If you guys have questions, feel free to email me. Like I said, I've been pretty responsive with emails. So if you need help, I think I'll have office hours this week as well. So thanks so much, guys. If you need advice, I'll always be there. And if you need help for medical stuff, I can help as well. I've had some students come back in med school and they were like, I need help on this. And I was like, oh, that's not that bad. Yeah, I can easily ask like first year stuff. Sure. Sure. Feel free to ask questions about the passage.